Welcome to Math with Michelle, where math finally makes sense. Whether you're tackling high school math or diving into college algebra, I'm here to break it down step by step with real examples and zero stress. From algebra to functions, graphs to equations, I've got it covered. Hit that like button and let's master math together. Welcome to linear approximations and derivatives. I want to bring the focus in on the word linear approximations. We are going to use a line, specifically the tangent line, to approximate some answers. So for example, without a calculator, how might we find out the square root of 50? Especially if, say, this was in pre-calculator times. So one thing that we do know is that if y equals the square root of x, when x is 49, y is 7. We know that ordered pair. Because 49 is close to 50, that's going to be my point of tangency here. Okay, I'm going to center everything around the ordered pair 49, comma 7. So my tangent line would be y minus 7 equals my tangent slope, x minus 49. Okay, so let's come over here and let's find our tangent slope. So we know that's technically the 1/2 power, right? So my derivative would be 1/2 x to the, I'll subtract 1, negative 1/2. And my derivative would therefore equal 1 over 2 square roots of x. So if 49 were input into here, I would have 1/14. So because of the derivative at 49, I have 1/14. Okay. So now I have a tangent line. Y minus 7 equals 1 over 14 minus 7/2, I believe. Let me double check that. 49 divided by 14, make it a fraction. Yes, 7/2. And then I'm going to add 7 to that. Got my x. And that's 7/2 again. Okay, so we have an equation of a tangent line. I actually prefer to do this up here, but I thought I'd give it to you here as well. If I want to find out what the square root of 50 is, and the reason why I like to do it up here is I like using this form better. Because now 50 minus 49 is 1. So I have 1/14 plus 7, or 7 and 1/14. I can get there here easy as well. Then I actually have to put 50 in and get a common denominator. Okay, so 7 and 1/14, right? That's what I got. Make that a decimal. What is the true square root of 49? 50. Is that close enough? Okay, that's up to you to decide. Now, can I use the same linear approximation for when x is 95? Let's check, does it hold true? One 1/14 times 95 plus 7/2. It says 10.28. We know the square root of 95 is not over 10. So there's more error there. And the reason there's so much error is I went too far from my ordered pair. In order to do 95, I would not want to use this ordered pair because it's too far off from my x value. Instead, I'd want to use this one. Okay, so the derivative is going to be the same derivative, but when I input my value, I'm going to get, whoops, 100. 100 has a square root of 10. There we go. Ooh. So when I put 100 into here, my slope will be 1/20. Y minus 10 equals, okay, I would rather have this, right? So negative 5/20 So we'll have negative 5 times 20, which is negative 5/20ths, or negative a quarter, plus 10 would be approximately 9.75. And if you look, that's really what it was approximately 9.75. So the neat thing is that if you pick a point of tangency close to your goal, 95 is close to 100, then the tangent line is going to get you close. Okay? Now keep in mind the square root function does this, right? So let's say we're here. The tangent line is going to be off faster than if we're over here. And that's because of the height difference versus the height difference. So the accuracy also has to do with how quickly the slope is changing. So again, this is called linear approximation using the tangent line. Now let's look at a couple things, and I want to compare dy and delta y. Okay, so I want to compare delta y and dy. So let's look at the function x cubed plus x squared minus 2x plus 1. And first, delta x, or dx, however way you're going to look at it, is going to be 0.05. And our goal is going to be around 2. Okay? So looking at it as delta y and delta x, meaning change in, 2 and 2.05. So x is 2, because delta x is 0.5, we're at 2.05. So we would have 2 to the third plus 2 squared minus 2 times 2 plus 1. That's 9. And what if all those 2's became 2.05s? Now we're at 9.717,625. Okay, so in this case, delta y was approximately 0.717625. Okay? And then I'm also going to come down here, since we're doing it already. I want to do delta x is 0.01. So 2 versus 2.01. Same idea. We're going to be looking at the same information. $9.140. So here we're off by 0.140701. That would be our change in y. So when we changed our x to 100th, our y was within 1400ths. Whereas before, when our x was in 500ths, our y was in 7200ths, approximately. Okay, so now we're going to come over here and I'm going to derive implicitly. So dy equals, I am going to, instead of writing dx after every one, I'm going to factor it to the end. 3x squared plus 2x minus 2 dx. Okay, now so this would be 3 times 2 squared plus 2 times 2 minus 2. 4, 12, 16, 14. So dy would equal 14 dx. Okay, and 14 times 0.05 is 0.7. And 14 times 0.01 is 0.14. So you can see here delta y and dy come out to be approximately the same thing. And that's because they're both measuring how far the variance is from y. Just one's doing it with formula-based and the other's doing it with order of pair based. But either way, we're getting approximately the same thing. So let's go ahead and look at that in an actual word problem style situation. So the radius of a sphere is measured and found to be 21 centimeters with a possible error of at most 0.05 of a centimeter. So their measuring tool must have measured to the nearest tenth. Okay, so they measured 21, but they could have been off by 0.05, meaning it could have been 20.95 or it could have been 21.05. It's somewhere in that window. Okay, so let's look at the volumes for each of those respectively. Okay, so if you recall, volume is 4/3 pi r cubed for a sphere. Okay, so 4/3 pi radius cubed. We'll start with the small one. 38,515.96. 21.00. I don't have to read. 38,792.39. So that was off by 276.4. Okay. I'll put that one there. 39,070. 0.134. So how much are those off by? $277.75. So one was about 277 one way and the other was about 277 the other way. So to safely say our volume, our volume is going to definitely somewhere be between these two numbers if we measured that. And of course, those are all in cubic centimeters. Okay, but what does it say if we use derivatives to help us? So dV would be 4 pi r squared dr. In our case, we found out that r was 21 and our dr was 0.05. To 77.08. So where do we feel like our error is? Do we feel like we want to do it by going, okay, well, here's what we expect to get. We could get as low as this or as high as this, and it could be off by 277 each way? Or do we just want to know, hey, it could be off by 277 each way? Now, depending on what we're trying to get to, since that's cubic centimeters, 200, is that an acceptable error? Well, it depends on your goal and what kind of fluids or whatever you're working with, on whether or not 277 cubic centimeters, I mean, that's 277 milliliters if you really want to think about it, and how much that it can be off by. So if going into it, you know that this error is too much for you, you're going to want to go back and you're going to find a device that has more accurate measurements than 5/100ths of a centimeter. Maybe 5/100ths of a millimeter might be happier for you. And that way you would have less error. So sometimes when we're working in science, that's something we have to think about, is that our measuring tools do cause us to have error because Maybe there's not enough little dashes for us to measure accurately. So until we get better accuracy with our measurements, our computations are going to have error as well.
Thanks for learning with me here on Math with Michelle. If this helped, give it a like and don't forget to subscribe for more clear and simple math lessons. Got a question or topic you want me to cover? Drop it in the comments. Until next time, keep practicing, stay curious, and remember, you've got this.